Okay, so thank you very much everyone for coming along to have a look at the work I'll be presenting today on laser crystallised thin film polycrystalline silicon solar cells. So it's a bit of a mouthful, but yeah, it's taken me 3 years to get my mouth around that and hopefully to get my head around some of the work that I'll be showing you. Just a quick note, as most of the work we're doing here now, this is also supported by ARENA through the Australian government, and also it's a collaboration with Suntech R&D Australia, and so a lot of the work gone into this is thanks to them as well, so we thank them for their support. Okay, so just to give an overview of what I'll be going through today, I'll start with the motivation for thin film, why we're looking at these type of technologies, and then I'll take you through some of the thin film PV technologies that are around quite broadly. Then we'll focus in on what we're doing here at the moment, which is this diode laser crystallised thin film silicon. And then I'll take you through a few aspects of those. To start with the material and device preparation, how we make these devices to begin with. Then I'll talk for quite a chunk about the intermediate layers, these buffer layers between the glass and the silicon, because as you'll see, these layers have quite a big impact on the performance of the device. And that also just happens to be the subject of my PhD, and so of course I spend 80% of my waking and sleeping thoughts thinking about this. But we'll leave some time to talk a little bit about the stability of the performance and some other current work. There's a lot of good work going on within our group by other members, and I'll touch on some of those. Before finishing up with some of the near-term priorities, what we want to do in the coming sort of year or two to improve this even further, and then looking beyond what we want to do up into the future to actually get this technology to a point where it is economically viable as a market entrant. All right, so let's get into it. Start with the motivation for thin film. And as most people here would know, the PV industry has been well dominated by wafer silicon crystalline photovoltaics for almost since its inception, way back when. And we can see here what happened leading up to 2008 with a huge demand in PV driven by feed-in tariffs and other incentives and the like, really increasing the cost of the raw material, the polycrystalline silicon, up to a peak of about 2008. And that really gave a bit of motivation for people to start looking at reducing the amount of silicon to either a very small amount or looking at other materials to get rid of the silicon altogether. But what we all know happened afterwards is that the supply of polysilicon came on, the demand for PV generally dropped off a little bit, and the price of polysilicon dropped off quite a lot. And not unsurprisingly, we see that the market for thin film followed a similar trend. So if we see here, the font's a bit small there, but we're going from about 3% in 2002 up to a peak of about 21% for all thin film commercial technologies as a proportion of the total PV market. And it peaked here at around 2009, and then it's also dropped off as that price in silicon dropped off and allowed the wafer-based crystalline silicon to really lower their costs and regain that market share. And so the challenge is on now for the thin film group to say, okay, if we're going to still stay relevant and if we've got something to offer to the market, we really need to not just offer a cheaper product, but it has to be high efficiency too. So it has to be almost equaling the crystalline silicon photovoltaics, but with that lower cost still remaining. And so that's what I'm going to talk about today, the way that we're trying to achieve that within our small group here. The next step, we'll have a look at some of the thin film PV technologies around. We saw here some of the major players in the market here during this heady phase. Really cadmium telluride here in this greyish block, and that's mostly First Solar, one of the most profitable PV companies of the previous decade. This block in the middle in the blue is SIGs, or copper indium gallium diselenide. And then on top of that, this orange yellow, that's thin film silicon, and that's mostly amorphous or micromorph silicon rather than what I'm going to talk about today. So those are the major commercial players that we've got here. But otherwise, and you see those up here, otherwise we have what I would call the research areas, and those are, well, essentially things that didn't make it onto that previous graph. They're things that are areas that are mostly still in research institutes but haven't really made a commercial impact yet. And just a few of those amongst many others are the CZTS, which is some work is happening here at UNSW on that, and that's essentially a similar technology as the SIGs, except it's using abundant materials. So it's not going to run into that problem that SIGs and cadmium telluride might have, and that they're really going to be limited by the availability of raw materials in the future. Organic photovoltaics and dye-sensitized photovoltaics is another area. There's some work going on here about that as well. And then there's thin crystalline silicon, which is getting closer to what I'm looking at here. But still within that, you see we have classes within classes within classes. We have a couple of options here. There's the wafer transfer work, and of course UNSW, with fingers in about every pot, is having a look at some of that work too. And that's essentially taking silicon grown on top of a high quality wafer, then removing that layer by various means and attaching it to a glass sheet before the rest of the processing is done monolithically. Quite differently to what we're doing, which is in the thin polycrystalline silicon, where we grow the silicon directly onto the glass substrate, which is similar as done in amorphous and micromorph crystalline silicon, amorphous silicon, sorry. Except here, afterwards, we have to crystallize that in some way. And there's a number of ways we can do that. The general approach in the past has been solid phase crystallization. This is the approach that CSG Solar took to the market back in the middle of the last decade, and the most successful approach for thin polycrystalline. And with that technology, they reached 10.4% efficiency, which was really the best at the time, but still they went by the wayside back in 2009, 2010 with many other thin film companies. But one of the problems with that was the open circuit voltage really hit a barrier at about 500 millivolts. And so the real, I guess, ideal of achieving the quality of crystalline silicon with the cost of thin film wasn't achieved with that technology, because that material quality roadblock, that 500 millivolts, really stopped it from getting the high efficiencies required. Other methods were attempted, such as aluminium-induced crystallization, done back here many years ago, but also in other parts of the world, and that hit a similar roadblock on voltage and therefore efficiency. So a few other methods are liquid phase crystallization, and this means taking the silicon up above the melting point, so that instead of just being frozen where the atoms sort of already are, they can move around in the melt and achieve a much better crystallographic quality. And a few ways of doing that are by zone melting recrystallization, which is done quite successfully over in Germany using a focused line lamp. But that's really heating up a large area and therefore requires quite a high temperature substrate and therefore a high cost substrate. But what's emerged recently in the last couple of years is E-beam crystallization and laser-based crystallization. And that really allows a low temperature substrate to be used. So we can achieve that high quality of the silicon through the melt, but we can still use something like glass. Within laser crystallization, again, there's more subclasses. And when I say the last couple of years, I lie, that's really been around for about 20, 30 years now, laser crystallization. But mostly with UV excimer lasers and visible lasers, really crystallizing very small areas at a time and achieving, therefore, small grain size. Whereas what we've done recently using infrared diode lasers is to pull large areas at a time and pull large crystals out of that, improving the crystal quality quite dramatically. And so now we're getting into the region that I'm actually going to focus on today and is the focus of our research here, and that's using this diode laser crystallized thin film silicon. So let's have a look at how we make these devices. And you can see here an image of the crystallization process in action. What we see here is our diode laser beam, that's about 12 millimeters long, and that's scanning across the surface of the silicon here to pull these large crystals out. And that's a continuous wave laser from the company Limo. But if we go back a couple of steps, you can see where we start, and we take this 3 millimeter thick piece of borosilicate glass. Onto this we deposit a boron-doped intermediate layer, and then we deposit by electron beam evaporation about 10 microns of amorphous silicon undoped. Now comes the all-important laser crystallization step, and you can see here two important things happen. So for one, of course, we crystallize the silicon and it becomes polysilicon rather than amorphous, but also the boron atoms diffuse out of this intermediate layer and into the absorber here, thereby doping it p-type. So we have our absorber layer created in one step. Then we etch back some of the rear surface to create a light trapping texture and diffuse an N+ junction by a spin-on dopant source and thermal diffusion. Finally, we passivate the bulk defects with hydrogenation, and there we have the end of our material preparation. If we have a closer look at that silicon, we can start to see some of the quality in it. So just looking at optical microscope here, we see the reflection of some of those crystal grains, and you can see we really getting up in length to several millimetres in length, and in the width ranging from tens or hundreds of microns, even up to a couple of millimetres in some stages. So the grains are quite a lot larger than what we've previously experienced in solid phase crystallised silicon, which was really limited to a couple of microns grain size. Within those grains, if you look at the cross-sectional TEM, you can see there's quite a lot of twin grain boundaries, which are mostly electrically inactive, so that's not so bad. And within those grains, there's really quite a lot of high quality silicon. We really can't see any defects in the good areas. And overall, we see the most defective areas are still below around 10 to the 7 centimetres square centimetres per square centimetre. And we're getting mobility measurements, judging by Hall mobility, getting close to that, or even above in some cases, the value for crystalline wafer silicon. So it seems that the quality of the material really is quite good. But if we move on now and have a look at how we create the actual solar cell out of this material, we take the structure that I showed you before, we add a thin layer of white reflective and isolating resist, and then we etch some holes through this layer so that we can then deposit by sputter aluminium over the entire back contact, and we can reach those N+ and P- layers respectively. Finally, we scribe the aluminium to separate those contacts, and there we have a solar cell. To end up, we do a simple contact bake at about 135 degrees to improve the quality of those contacts. The whole thing is in superstrate configuration, so you can see the sunlight here coming through the glass, through that intermediate layer, and into the absorber here. So that, again, puts a few constraints, a few requirements on our intermediate layer here that you'll see in a minute. Okay, so now I'll take you through to some of our results, and to start with, I'll take you through to our best results so far to see where we've gotten to. And this is it. You can see 11.7% efficiency, which is really quite exciting for us because that's well exceeding the previous record for thin film polycrystalline silicon solar cells, which, as I mentioned before, was held by CSG Solar at 10.4%. But even more exciting is what we see here. I mentioned that 500 millivolt barrier that we really couldn't get through after years and years and many researchers' efforts. And within a couple of years, we've got up to 585 millivolts. And that's the most exciting bit because that really shows us, okay, there's a real breakthrough in material quality. This isn't just an incremental improvement, but this is a different material altogether and opens up a whole new world of research for us. But we'll go through now and have a look at how we've got there, because we've only been doing this work for about 2 years or so, and we've really come a long way. So we started here with our first ever devices with the help of Suntech R&D Australia, getting to about 6.5% 2 years ago. And at that time, we've really improved fairly consistently up to where we are now, to almost 12%. And it's interesting when we look at how we've got there, and it seems most of the improvements have been due to that intermediate layer that I mentioned before. We started off here using a simple silicon oxide layer, and then we've made our first improvements by going through to a stack of oxide, silicon carbide and oxide, which gave us a bit of an optical boost through an antireflection effect. We improved even further by changing that to an oxide nitride oxide. And then finally, we improved the nitride layer itself by depositing it slightly differently and got a big boost there. And then finally added some rear texture, which is, as you see, the only point on this graph that's not related to the intermediate layer, and gave us our final boost up to where we are now. So it seems that there's quite a big impact from this intermediate layer, and that's why I'm going to talk a lot about that. So you see here, this is what we're talking about between the glass and the silicon there, this buffer layer. And it's not surprising that it has such a big impact when we look at all the things this has to do. So it has to be a wetting layer between the glass and the silicon so that in the molten phase, the silicon sticks to the glass and doesn't just ball up under its own surface tension. It needs to be a dopant source, as we saw for those boron atoms, to diffuse out into the silicon. It also needs to be a contamination barrier, because if boron's going to diffuse, then other things are going to diffuse. And we need to control that amount and make sure that no nasties get into the silicon layer and affect the lifetime. We need to be stable at above the melting point of silicon, both mechanically and chemically. And of course, it needs to be a transparent anti-reflection coating because we are in superstrate configuration. It also needs to be a passivation layer because we're on the side of the silicon here, on the front side of the silicon, and we need to keep the front surface recombination as low as possible. So if I take you through those one by one now, we can, well, first actually, let me show you the materials of interest that we're going to look at. So silicon carbide, silicon nitride and silicon oxide, as you saw before in that previous graph, are the main ones we've been looking at so far. And they appear quite a lot in the literature in this type of work in terms of being wetting layers and barrier layers and so on. And we've been depositing these layers either by RF sputtering or by PECVD. There are a number of other ways you can do it, but that's what we've had available to us here. And generally, most of the things that I'll say today are fairly independent of whether we use one or the other of those methods, which is actually quite surprising when you see what the results are. The layers are up to about 200 nanometers thick, depending on how we do them. And as you saw before, we either do them alone or in stacks, incorporating one or more of these materials. So let's go first and have a look at the results of the wetting layer analysis. And what we see here is that there's a few different modes. And looking at firstly what laser energy we use, we can map out a process window, because essentially the only way you can assess the properties as a wetting layer is to see how large the process window is between the point where it begins to crystallise, which is here, and you can see if you're too low, you get these nanocrystalline regions, and it's really not the large grains we're looking for. You see some large grains in the middle here, but it's not really a regime that's good for us. If we're too high, then this de-wetting occurs, and that's the problem that this wetting layer is trying to avoid. So you get the silicon balling up into these large clumps here and peeling off the silicon away from here. But what we want is this middle region, just right here, where we're drawing out these nice large grains. And that's how we're defining this process window, and therefore which wetting layer is best. And for example, if we look at this table here, and I show you the process range simply shown here in joules per centimetre squared in terms of laser energy that we can apply. If we have no intermediate layer at all, and simply put the glass directly on the silicon directly on the glass, we see that we have a very, very small range. It can work, yeah, but it doesn't work very often. We often get this de-wetting, at least in some areas of the strip. But if we add these intermediate layers, that improves quite a lot. Starting with silicon oxide, the nitride is even better, and the silicon carbide is best in what we've seen so far. But it's good that at least they all work some sense, so we can use any of those that we like. Even if the carbide is the best, the silicon oxide will still give us a good result. But there is a slight issue with the nitride, and that's that even within this range here, we get some pinholes that start to occur at the higher laser energies. So it's a bit hard just to simply quantify the wetting effect only by this process range, because with the nitride we are a bit limited, and those pinholes are really something that we don't want and can cause us problems in the further processing. Okay, so next I'm going to talk about these layers as a dopant source, and once again I show you what we're trying to do here. The boron is diffusing out of that intermediate layer into the silicon to create the absorber. And if I can explain this graph for a second, it's essentially showing a Sims profile of the boron concentration after crystallisation. You can see here, this is the glass side, and here is all the silicon going into this interface here. So here is the air side over here. And what we see is that we get a uniform region created here throughout most of the thickness, and that actually extends back beyond here to the air surface. And that's occurring because in the molten phase of the crystallisation, all the dopants that are in the silicon are going to diffuse very quickly and become a uniform distribution. However, we thought we saw here a P+ region at the interface, and perhaps explain this by additional diffusion during the solid phase as it cools down from that 1400 degrees, which would be quite useful because a P+, as most of you know, would assist with reducing surface recombination. However, we're not quite sure that exists, and when we tried to verify this using conductivity measurements via spreading resistance, we really didn't find this P+ region. You can see here again this uniform layer. If we're looking at carrier concentration here, about 10 to the 16 p-type, what we see here is instead of increasing and creating this P+ region, we actually see a decrease in the p-type, and we start to see it turn n-type. So we get some sort of inversion layer effect, and we really don't know why that's occurring. There's one theory that perhaps as the silicon cools, that glass is actually acting as a sink for the boron and it's sucking it back in. But we really need to investigate further to see what's going on here, because if we can control and manipulate this interface here to get the profile we really desire, we could gain a lot in terms of improving that passivation there. Okay, the next thing I'm going to talk about is this layer as a contamination barrier. So we've seen that we want the boron to diffuse into the silicon, but using borosilicate glass, we have a whole bunch of boron already in there. And it actually turns out that the problem is the other way around. We have difficulty stopping the boron from getting into the silicon, or stopping too much getting in, more than the doping that we'd really require. And what we see here, if you look at the sheet conductance I put on this axis versus various intermediate layers, we really want that level to be down below about 1 millisiemens, so below about 1,000 ohms per square in terms of resistance there in the bulk. And if we have no intermediate layer at all, of course, way too much boron diffuses into the silicon from the glass, and we're way up here at 100, and we don't want to be there. If we add an oxide layer, then around 10 nanometers is simply not enough. It doesn't really provide much of a barrier. But if we go down to 80 nanometers, we can start to see now we're in the right range, and beyond that, it's similar to 200 nanometers here. So somewhere between 10 and 80 seems to be where we're really starting to get the effect we desire. If we use a silicon nitride, we see we're just on the cusp of that. We're really not below that threshold where we want to be. And that might have a little bit to do with that pinholing effect I mentioned before. If we use a silicon carbide, again, it depends on the thickness. So a thin layer here, again, we're really not achieving the barrier effect. And with a thick layer here, 140 nanometers, we're almost getting there, but still not quite. But the good news is that we can simply use a stack of these materials. So if we want the barrier effect, we can use the silicon oxide. And then if we want the wetting effect of the carbide or the antireflection effect of the nitride, we can simply add that on top and have a glass oxide nitride silicon stack or something of the sort. Okay, another thing that can diffuse from the glass is iron or other contaminants, and so we had a quick look at this as well. And we can see here again, looking at the SIMS, the glass over here, and the silicon over here, we can see if we measure within a crystal grain with no intermediate layer, we see it doesn't look like we have a problem. This is below the detection limit of the of iron and SIMS, so we can see just here random noise. However, if we look at the same thing at a grain boundary, we see what we consider to be an iron precipitate here. So this iron concentration jumps up quite a bit at this region here when we measure at a grain boundary. And so what we do is see if this oxide is good enough to keep out the iron, and that looks to be the case. In this yellow curve here, we see measuring again at a grain boundary, but this time with a silicon oxide intermediate layer, and we see again we're down here below the detection limit of the measurement. So that's enough to satisfy us, at least in the first case, that iron's not a problem if we use this oxide barrier. Okay, the next thing we want it to be is stable at the melting point of silicon. And first we're going to have a look at the mechanical stability, and this is the actual looking here under optical microscope of the interface between the glass and the silicon, or at that intermediate layer. And what we see here is when we use thick silicon carbide layers, we get quite a lot of wrinkling, suggesting that there's a bit of stress going on there or something's happening. The same occurs with the nitride, a bit of a different pattern, but we still get some wrinkling effect there. But if we use an oxide or a thin carbide or no intermediate layer at all, we get a nice flat surface. Now we don't actually know if this wrinkling is bad or good, maybe it's even good. But it's an issue that we need to look at, and again a difference between these layers. So it gives us a hint of something that we might need to investigate to see whether it's having an effect. So the other point of stability we need to notice is the self-stability of the intermediate layer components itself, so the chemical stability of the elements. And what we see here is that when we look at the nitrogen concentration, again after crystallization, measuring SIMS, this is the glass side over here, this is in the silicon, we see that the nitrogen, when we use a silicon nitride barrier, really peaks up here. We're getting to almost 10 to the 20 in concentration of nitrogen atoms in the silicon. And that's really not ideal, and that's showing us that that silicon nitride layer itself is not entirely stable, and some of it's moving around and contaminating. We know that's not just from the background anyway, because it doesn't occur if we use a silicon carbide or silicon oxide intermediate layer. And also, if we measure the carbon or oxygen concentrations, they're not affected by these layers, and they're simply determined by the background concentrations. So that's another issue we need to look at. Okay, we're getting down to the next step is the anti-reflection coating, and of course this needs to be transparent to let the light through. And so we can have a look at that here by looking at the different layers we've investigated. And ideally, between the glass and the silicon, we'd like to have the refractive index of about 2.4 to minimise the reflection, and the thickness as determined by this equation here. And of course we want no absorption, because if we have parasitic absorption in this layer, those are photons that aren't making it through to the silicon, and therefore we're losing photocurrent that we would otherwise have. So again, we have a look here at the various layers, and in the red here, that's a almost 50 nanometer thick silicon carbide layer. The refractive index is kind of good, but here way too much absorption. And even if we go down to a 14 nanometer silicon carbide, again, still in the visible, we're getting quite significant absorption of light. And so that's stealing a lot of those useful photons that we'd rather have in the silicon. If we go to a silicon nitride layer, this one's 80 nanometers, so roughly what we would have as an anti-reflection coating. We still see quite significant absorption at the lower wavelengths, so below about 500. Those are still useful photons, quite a lot of them still in the solar spectrum, that we're stealing from our device. And if we look at the oxide, that's completely transparent. So here we show in the white here, that's the curve for the borosilicate glass itself. So that's absorbing a little bit here below 350. And the silicon oxide lays over top of that, so that's completely transparent and doesn't affect the optical properties. Now, just recently we've managed to optimize that silicon nitride layer to reduce the absorption, and that's fairly well-known methods to do via PECVD, and there's usually a trade-off between the absorption and the refractive index of silicon nitride. And we've also done that by sputtering, by changing the way we sputter to do it reactively in a nitrogen environment. We've also slightly reduced the refractive index, but quite significantly reduced the absorption. And so from an optical perspective, that's much better, and that's led to our latest efficiency increases. Okay, now getting towards the end of this intermediate layer discussion, we're looking at the passivation quality. Now this is quite difficult, and this is something that's plagued me for the last few years, because I'd really like to be able to measure this interface and understand what's going on here in terms of the passivation quality. But because of that thick glass layer, we really can't get to it. So we can't really make MIS structures and measure capacitance voltage, for instance, to assess the interface defects or the charging component here. So all we really have at our disposal is to make solar cells and then measure the spectral response in the IQE. And so that's what we've done. And I can show you here a few results. If we compare, to start with, an oxide intermediate layer, so here glass, oxide, silicon, with a stack of oxide and carbide, a very thin carbide layer, here with a stack of oxide and nitride. And so we can get an idea. Again, this oxide is the same in all three, so that's acting as a barrier layer. And these other layers here on top are showing us what's happening here at the interface. And now if we look at the IQE, we can see quite a drastic difference. So in the white, first of all, we see when we use a silicon oxide intermediate layer, and the IQE is quite okay, getting up around 90% here at the plateau, down to fairly low wavelengths, so we're losing a little bit down here, but generally fairly good. And that indicates a reasonably good surface passivation and a good low level of surface recombination. But if we look at the oxide carbide stack, with the carbide in contact with the silicon, we see here very poor surface, and the IQE is dragged down quite a long way due to that, or we believe due to that surface recombination. So that's really undesirable. And the nitrides stack isn't even shown there because it was so bad that we couldn't get reliable IQE measurements. So that's really not very good and not desirable, because our silicon oxide with its refractive index of 1.5 isn't adding any anti-reflective benefit. So we'd really like to be able to use the carbide or the nitride, and we have to find a way to do it. Our solution was to use triple layer stacks. So you see here, we've changed these now. We've got the oxide and carbide, and then we add a very thin layer of oxide again on top of that, between here and the silicon. The same with the nitride, triple layer stack of oxide, nitride, oxide, or O&O for short, in the hope that if this oxide is very important to having contact with the silicon, maybe this stack will get us there. And these layers are kept nice and thin so that the optical properties are still quite good. We actually still get quite a good anti-reflection response out of this, and even here we get a much better anti-reflection coating than had we had this thin layer of carbide on its own. So let's have a look at the IQEs now, and we see a vast improvement. Again, we've got that oxide alone here in the white, representing that baseline case, and now we have a look at the yellow. That's that oxide, carbide, oxide stack, and that's come right up to the same plateau level. We've got something of what seems to be a bit of a dead layer here at the front, so we're really not quite sure what that is. But certainly overall we've improved the lifetime. The surface, we still need to investigate whether there's a bit of an interaction going on there, or maybe a bit of a mixing of the components there. In terms of the ONO, the nitride stack, where we've improved quite a bit, but still not quite there. Again, we see the IQEs dragged down towards the short wavelengths, indicating again that there's some issues at the front surface. So although we have that oxide there, it's still not doing everything. And there's a few possibilities. Maybe we're still getting some of that nitrogen contamination coming through that oxide. Maybe it's not thick enough to act as that good passivation layer. We're not quite sure. But what we can do is experiment and play around with the layers. And that's what we've done here. And that's using this optimized ONO, again with this reactively sputtered silicon nitride layer. So not only did this reactive sputtering decrease the absorption, but it also increased the IQE. And I should point out here that these IQEs are calculated to take into account the parasitic absorption. So that effect is removed from here. So we're not just seeing here a lack of, we're not seeing this drag down because of parasitic absorption. This is actually what's coming out of the silicon itself. And we've improved it quite significantly by using this optimized stack. And that's what's led to our latest efficiency records. But you can see there's still quite a bit to go. We can improve that peak IQE even further and hopefully eke out a little bit more efficiency from there. And of course, ideally we go all the way up to unity. And so that's something for the future to try and improve the lifetime in this material. And just for completeness now, I'll show you the rest of that spectral response. So here's our best cell here, and we see the EQE in green, and also the reflectance here in red. And so this shows you that that is acting reasonably well as an anti-reflection coating, with the minimum down here somewhere in the visible. But there's still a long way to go here. And by improving the light trapping in general, we can hopefully reduce that reflectance and gain a bit more in current. Okay, so I've got a little bit of time left, so I'll talk about the stability of this work, because we can't really show you these great 11.5% results without admitting that we do have some degradation occurring. Okay, and so here again we see our best result, 11.7%, and that's measured directly after the final contact bake to improve those contacts. But if we leave that for a couple of days, this is what happens, and we drop down mostly in fill factor, a little bit in open circuit voltage, and we end up a couple of percent lower absolute. And so that's really not ideal, and we need to work out what's going on there. And one thing we can notice is that that efficiency drop is completely recoverable with rebaking. So if we do that contact bake again, we recover all of that efficiency that we lost, and even some more. You can see these closed circles here representing measurements taken after a bake, and the open circles here in the subsequent days thereafter. And so interesting to note that this occurs in the dark, so it's not a light-induced degradation, as might be commonly seen in amorphous silicon and even to some extent in crystalline. And it also seems to be related to the absorber doping. So here we show you another cell. So this is our second best cell, and you can see here the final efficiency is very close to its initial efficiency. And in fact, that's our best stabilized efficiency at 10.4%. And the main difference between these two cells is that the green one here had a slightly higher absorber doping, and so we think this is related to that degradation. And if we look at here, it's easy to see why, because we're making contact between sputtered aluminium and quite a lightly doped absorber layer, here only 10 to the 16, oh it should be 1 e to the 16, I'm sorry. And so everyone who makes silicon solar cells knows that's not really an ideal device structure. To get a good contact here, we get all sorts of problems with Schottky barriers and the like. And so the simple solution to this is to add a P+ layer underneath this. And we do that by additional masking and doping and diffusing. And that's something that Chaho has been doing in our group and having quite some success with. And you can see here an example using some of our other material, not our best material, but at least good for comparison, that our efficiency in the baseline scheme, we see that degradation occur as we saw before. But if we use this selective P+ scheme, we see that still stable after a week of being left with no rebaking. So that's a proof of concept that this tends to work, and we need to simplify this a bit and then apply it to our best material and hopefully achieve stable efficiencies above 11 or even 12%. Okay, so I'll move on to some of our other current work. And I'll start with the rear texture. I mentioned earlier that the rear texture has already been implemented into our best devices. And this is something that Zamir's been working on and just started and hopefully going to take this even further. And as I showed you before, we etch off some of the back here. And this is what it actually looks like. If we look at the AFM, we can see that the RMS here, about 78 nanometers, a good texture right through, quite random, so that's quite nice as light trapping. And if we look at the absorption curves, we can see the effect this has with the white here, the absorption in just a silicon without a back reflector, measured after this back texture is applied. So it's really improving our long wavelengths that might otherwise go straight through the back of the silicon or come back and go straight out the front again by increasing that path length. And you can see that happening here when we look at that light moving around, getting another chance here, perhaps being totally internally reflected off here, and having a much longer path length through the silicon. However, that's only addressing the long wavelengths here at the back. But we have this reflection here at the front that's occurring through the entire spectrum. And so ideally we'd like to address that as well. And one way we can do that is by adding a texture onto the glass itself. And that means that anything that's reflected from this layer here has a chance of being totally internally reflected at the other side of the glass and having a second chance to get into the silicon. And so that's also something that Zamir is going to be working on the next couple of years that would give us a big boost in current if we can achieve it. Okay, another aspect that we can look at is, it becomes apparent when we look at sun's VOC curves. So if we look at the sun's VOC measured at the material stage, so this is before we do the metallisation, we see it's quite good, almost n=1 recombination, indicating very good material quality. But if we measure again after the metallisation step, we see that quite a lot of n=2 comes in, and also here quite a big shunt component, about 500 ohms centimetre squared of shunt. And we really need to eliminate that because that's dragging down our efficiency through dragging down the fill factor. And if we look at dark lock in thermography, we can get an idea why, because we see here this hot spot occurring coinciding with a crack that's running through the silicon. And that's the same in both forward and reverse bias, and that indicates an ohmic shunt. And these cracks are something that occur during the crystallisation process. As we scan from bottom to top here, we see these cracks through the silicon occurring. That occurs quite repeatedly on essentially all the cells or all the devices that we make. But something that Jia Liang's been working on is to remove those cracks by adjusting the laser processing. And he's been quite successful already in doing that. And you can see here just a couple of fine cracks at the edges, but through that main region, we've got no cracks. And so that's something that he's improving even more, and hopefully can get rid of those cracks altogether and then eliminate that shunt problem. Now something else completely different, a bit of white to wake you up. But if we look at the grain orientation here, this is something that Jay's been working on. And we can see here, if we look at the inverse pole orientation map, we've got our 1, 0, 0 here, 1, 1, 0 here, 1, 1, 1 here. We see a bit of random orientation here, maybe a preference to 1, 1, 0, but a bit of others as well, a bit of random. What he's been doing is looking at adding a silicon oxide capping layer, so this is not the intermediate layer, but on top of the silicon on the air side before crystallisation. And with that he's had quite some success of making very repeatably 1, 0, 0 orientated grains. Now, we're not sure yet whether that's going to be a big boost or not, but certainly it's something that's quite different. And we've seen before in photoluminescence images that their best grains have been 1, 0, 0 ones. So perhaps that would give us an efficiency boost further than what we've had already. Okay, laser diffusion. So we saw before that our diffusion is done by spin-on dopant and thermal annealing, but there's another way to do it by laser diffusion. And the advantages is that it's much cheaper. Okay, so we don't need a big furnace. It's much, much faster. So a long furnace process is really not ideal, particularly in production environment. It has no effect on the glass because if we do a total RTP or RTA anneal, the glass softens, whereas that doesn't happen if we're using lasers because again, we're only heating up the silicon itself. That also has a big impact on those cracks that I showed earlier because if we're softening the glass, that can move around where those cracks occur and exacerbate those cracks, make them wider and worse. But the only downside is we're not sure if we can control the process window because we think with a RTP process, we dial in whatever we want, everything's the same temperature, easy to control. But the great work that Mega has done has shown that it's actually the other way around. Using our standard RTA processes and an improved RTA process, we still, throughout different strips that are identically processed, get a large range in sheet resistance here. You can see these blue here, and green here, showing us a lot of variation in that sheet resistance measured by 4-point probe. But using the laser diffusion process that Mega's come up with, we see a very stable sheet resistance. And that's really turning this negative into a positive here, ticking all the boxes for laser diffusion. And that's something that we want to implement very soon in our BESS devices. Okay, so nearing the end, so I'll talk quickly about our near-term priorities. And so the first thing to do, of course, is transfer all our processes to the TTB. So at the moment, we're based down in Bay Street. That means we're going to be ramping up a lot of new processes, a lot of new tools over here. So that will be the first priority. Of course, then we want to improve the bulk passivation. That's something that's already happened, and Kyung has been working on that. To go into the detail would take me another half an hour, but I can simply let you know that he's already had some improvements. And of course, if we match that up with some of the other work going on in bulk passivation here at UNSW in the first gen group, I think there's a lot of bonuses to be made there. Then there's the surface passivation. So I mentioned the glass side, but on the air side, there's still perhaps some bonuses we can make there by improving that passivation. We need to identify and address the other device fabrication losses. So as I mentioned, we've got that shunting issue with the cracks, but we've also got things like this cell isolation scribes. And this is done by laser to isolate the cell area. And we see here quite a lot of damage coming around there, poking through that isolating resist layer. And so that's something that may be responsible for some of those n=2 losses I showed earlier. We have a possibility of investigating alternative junction formation. We've already shown the laser diffusion that Meg has been working on. But there are perhaps heterojunction options. And our colleagues in Berlin have been working on that kind of thing and having some great results. Or otherwise, our colleagues in Jena in Germany have been doing this by excimer laser epitaxial crystallization of an amorphous doped layer and having some really good results there. So there are a large number of different options we can look at there. And of course, we have some good results in plasmonic light trapping here at UNSW. And there'd be the possibility of applying that to these thin film cells and really improving the light trapping there. So quickly to finish up with the long-term priorities, and I'll show you this simply by some simple economics, some back-of-the-envelope economics, to really show what our long-term priorities might be. Because if you look at the multi-wafer spot price, remember the whole idea of this is to reduce the cost of silicon by using thin film. The spot price at the moment, that I looked last night, was about 84 cents a wafer for multi. If we assume maybe 17% efficiency, that works out at about 20 cents per watt. Those more involved might correct me, but as a back of an envelope, that'll do. Now, if we look at borosilicate glass, which we're using for this process, at last count, that was at least $20 per metre squared more expensive than standard solar glass for most solar manufacturers, possibly more. And then if we calculate that, assuming roughly 12% efficiency, we can see that that glass increase alone counts for an additional 17 cents per watt. So we're really eroding almost all of the advantage that we create by getting rid of that silicon. And then we have a lower efficiency product. So at the moment, it's not really adding up. But that makes quite clear what we need to do long term over the coming years. And that's either to increase the efficiency quite dramatically, and as you've seen, we're working on ways to do that, or, and rather more ideally, use standard glass. So to move these processes away from the high temperature borosilicate glass onto the standard soda lime glass. And that's something that we might consider in the future. Another thing to point out about long-term priorities is the process sequence. So a typical thin film amorphous silicon process sequence looks like this, whereas our sequence at the moment looks like this. And so, of course, we're in research mode, so we don't want to get too down on ourselves at the moment. This is what all research does. But long term, we can see that this long device fabrication process is going to bring opportunities for problems, for instability. In manufacturing, of course, the more tools you have, the more issues you're going to have, the more CapEx and OpEx you're going to have. And so that's something long term, not in the next couple of years, but we have to keep in the back of our minds, always looking at options to simplify that contacting scheme. And the great thing about this material now is that as we get more improved material, we get closer to wafer silicon work, and we get to piggyback off some of the work that's going on in perhaps the interdigitated back cell concepts that are really taking off now around the world. And so we can really work together with our wafer friends on this sort of work. Okay, to sum up, nearly out of time, so we'll go through laser crystallized polysilicon solar cell we've made, reaching 11.7% efficiency, exceeding the previous record for thin film polysilicon cells. We have a short-term recoverable degradation, but we've managed to create a selective P+ metallisation scheme that can make stable cells. Our performance improvements over the last couple of years have been mostly due to the intermediate layer. But the real important thing, and as I've tried to show with the last half of that talk, is that we have a lot of other work going on that's producing some good results now that can add on top of this result already. So we expect this to increase even more so in the future, hopefully achieving those high efficiencies that we need to be really economically viable. And with that, I'll thank you for your attention, and hopefully we have time for a couple of questions. So thanks very much.
Open for questions. There's a question over there.
Thanks for a really great talk here, Jonah. Really interesting. So I have a couple of questions. If you can address one or both, or neither. So I don't make silicon solar cells, and the point that you raise about degradation of the EQE due to the contacting, I can see why having selective doping around the contact would improve the EQ overall, but I don't understand why it would impact the degradation, or I don't really understand what the degradation mechanism is. So I wonder if you can explain that.
Yeah, the short answer is neither do we. One thing I'll quickly point out is that it's not degrading the EQE. It's quite interesting that the EQE and IQE are staying stable. So when we look at the current overall, that's not being affected by this degradation. It's mostly in fill factor and voltage. Now, one point of that is we understand that at lightly doped contacts with aluminium, we get a bit of a Schottky barrier there, and that's going to affect the voltage and the fill factor there. But why it would change with baking and non-baking is not quite clear. Why it might get better is clear, because if we give it a nice anneal, that's okay. But then this transient effect is really not quite understood. So at the moment, our approach has been it's actually easier to fix it than it is to understand it. So that's why we've gone for this P+ contacting scheme. But that's even more complicated than the list I showed you before. So ideally, we'd like to get rid of it altogether. But yeah, any ideas are welcome. Yeah.
So is the degradation that you see with the aluminium contacts when you don't have the P+ region there, does it depend on whether current is passed through the device? Does it degrade faster if you've got current passing?
That's a good question. We haven't tested that in any sort of way. All we've done so far is simply do repeated measurements over days. But as far as actually having it active with current passing it through over several days, we haven't seen that. Certainly, if I measure it and measure it again several times in the same, over the same small period, it doesn't change. But it's only sort of leaving it for another, even an hour or so, even half an hour, we already see some degradation beginning. So it's again something we could look at. Yes?
You show your results comparing the double layer stack and the triple layer stack, and the oxide nitride performing worse than the unknown stack. So if you replace I understand it's a sputtered nitride.
That's right, yeah.
Stack. So if you replace the sputtered nitride by PCVD nitride, do you think it may improve the performance of the double stack?
I'd hope so, but one of the interesting things is that with a sputtered a PCVD nitride, we had problems with the crystallisation. So again, all these layers can mildly affect the wetting properties, even if they're the same material deposited by different means. And so when I used a PCVD nitride, I actually had quite a few sort of almost microcracks occurring in the intermediate layer itself. So I wasn't able to get material that was good enough for a device test. I'm still looking at that, and hopefully we'll have time to complete that study before I finish my PhD. Yeah, but certainly if we've seen such a big difference just by changing the way we sputter a nitride, you would expect to see that there's potentially much more improvement to be gained if we can understand it and then dial in what the ideal is. Yeah, sure.
You talked about the texturing on the glass.
Mm-hmm.
So if you texture the glass now, would it affect the laser process?
Yeah, we assume so. So we have done a couple of tests, I guess, a bit of a toe in the water test. So I've done one quite a couple of years ago now, and Bonnie Eagleston did a little bit of work that essentially showed this is in principle possible. So we could get crystalline silicon, a bit of de-wetting, a bit of problems, a bit of roughness, additional roughness occurring. But in principle, the crystallisation can occur properly on a textured substrate. And in fact, our colleagues over at in Berlin who are working on e-beam crystallised silicon showed a nice paper last week at the IEEE conference where they've done the same thing. So they've crystallised textured substrate quite nicely using the e-beam crystallisation. So we're quite confident, and I think Izmir is going to have a lot of success with that over the next couple of years. Any more?
I have one question. A couple of questions.
Great, yeah.
First, I noticed that when you use the double layer for the intermediate stack, the long wavelength EQE also improved in the case of the.
Good. We've got a train spotter involved. Yeah.
Interesting.
Yeah. Okay. So I cheated a little bit there. So that one, if you recall way back at the start when I showed that improvement graph, the last step had the improved ONO stack and the rear texturing. So when I showed that, I won't try to find it here, it'll be too far back. But that's the IQE was slightly better for that final point when we added that rear texture. And that I believe is, we're also avoiding some of that light, that long wavelength light, ending up in the resist layer, where we have some parasitic absorption there. So by improving the reflection back into the silicon, not allowing so much to go straight through to that resist layer where we get more parasitic absorption, that improves that IQE, because that parasitic absorption is not accounted for when we do the IQE, but well noticed.
One more, probably following through this, because that resist seems to be very important to be able to place that bottom contact all the way through without shunting your emitter. So how is that done? How can you open the bottom only and deposit the metal?
It's done by firstly inkjet opening of the resist layer, and then etching through the silicon using a wet chemical etch process. And then finally we do a reflow process. By exposing that resist layer to solvent, we can flow the resist back over those walls and cover the emitter. That's done. And that's simply the old CSG process. So a lot of this process is really standing on the shoulders of CSG Solar. And that's why we've come such a long way so quickly, because we've already had all that bank of work done on it. But what we're getting to now is that I think we're reaching the point where we need to move further. If we want to actually go on beyond, apart from our material improvements, if we want to go on improving our device, we need to start looking at other options that may be getting away from this resist layer, because that's restricting us to some low temperatures, and perhaps moving more towards some of the work that's going on generally in wafer-based IBC cells.
It's time for one more question.
Craig, did you still have one more?
Yeah, I did. I was near the end. You alluded to some process improvements with the laser tube that have resulted in fewer cracks. And I was wondering if you could maybe elaborate on that a bit, or if that's not something.
I'm not sure. Sergio, are we talking about that yet? Jielang's work on on exactly what he's doing to.
No, it hasn't been reported. It's just simply by varying the speed of laser head.
Yeah.
So there's no model. We don't understand how it works. It's just we
Yeah.
trying faster, trying slower.
That's it. I mean,
more
obviously,
power, less power.
you have effects there with the thermal expansion. You've got the silicon expanding, and you've got it going through phase transformations. You do have a bit of glass heating at the very surface. So we've got all those sort of things there that can occur, that can cause some stress to occur and some cracks to open up. And yeah, but just by changing the small amount of parameters we have available to us, I can tell you that it's not changing the actual optics of the laser itself. It's still coming out of the same laser head. But by changing things like the speed and the focus and so on, he's been able to achieve a better result. So very, very mild changes, not major ones.
What is important here, that cracks occur after silicon solidification. So we see that cracks are just going through the middle of crystals or with sharp edges, which means that there's one more motivation for using textured glass. We know from ISPC silicon that stresses are less in textured films if we manage to develop process, to transfer the process to textured glass, then I think that cracking is a lot less likely.
We've also found that by de-stressing the silicon to begin with, by putting those isolation grooves in the silicon before we do the crystallization, then the stress is already relieved. So there's a critical width, I guess, where you can have silicon crystallize without it cracking. So there's a few options there.
Okay, one more question.
So how wide can these laser passes be?
At the moment, it's determined by the laser that we have, which is 12 millimeters in width. But Lima, who make the laser, they already make a 30 millimeter wide beam, essentially exactly the same, and they claim to have the same homogeneity over that length. So we could go up to there, and they claim that it's scalable up to meters in length. So, yeah, what the cost of that laser looks like, you know, I don't want to think about just now. So it might be in the future a better option to. It depends when you order, and yeah. And so it might be better to look at what happens if we stitch passes together. So that's a bridge we need to cross when we come to it. But at the moment, we're simply making our entire cell within that one pass, so we don't have to worry about the edge effects just now.
So what size are your cells?
Our cells are 1 centimetre squared. Well, they're, to be perfectly correct, they're about 6 millimetres by about 1.6, 1.7 millimetres. Centimetres, sorry. 0.6 centimetres by 1.7 centimetres.
Can I just ask a quick last question? You said, have you tried any other substrates? I mean, you mentioned like BSG. Like I think last time we tried, when I was testing with the laser, we used the quartz. Have you ever tried using quartz as a substrate? Or?
No, I haven't, because that's it's tempting to look at what happens there, but it's sort of driving us down the more high temperature path. So yeah, it's always tempting to see if we can get a better result by looking at a pure quartz substrate or by different types of glass. But it's something that's, you know, then frustrating because we just have to go back again. We see really, for what we're doing here, no long-term future for moving to more expensive materials. What I have done is look at going to soda-lime glass, as I mentioned. I've done some small experiments just to see if it works. In principle, it works. But there's a lot of challenges with the changed expansion coefficient with that type of glass, and so it's a real engineering challenge. But other substrates, it's possible. It's a lot of things haven't been tried yet.
Okay, well, I would like to thank again Jono for this excellent talk, and thank you very much for showing this amazing.
Thanks for coming.